how magnetic moments in a helical edge state can make weak correlations strong.
Okay, good afternoon, and thanks for the introduction, and also thanks for giving me the opportunity to show this work here. This project was a collaboration with Florian Geisler from Würzburg and my advisor Leonid Glassman and me, of course. And I would also like to acknowledge Moshe Goldstein and Yuval Geffen. So we have already seen topological insulators here. I will still introduce the system again. So I will be considering a two-dimensional topological insulator, or 2DTI in short. This system supports gapless helical boundary modes, and the fact that they are helical means that basically the right movers and the left movers are Kramer's partners. And because of this and the fact that they are fermions, there is no elastic backscattering from one state to the other. And therefore, the conductance of this kind of sample is quantized at zero temperature, quantized to E squared over h per edge. And at finite temperature, you can have inelastic backscattering, and this will reduce the conductance below the quantized value. Okay, and how about experiments? I will talk about a very specific experiment from Ru Du's group at Rice in collaboration with Peking University. And here they measured the conductance of an indium arsenide gallium antimonide 2DTI. And here is the conductance as a function of temperature. And what is striking here is that it shows insulating behavior. Namely, when I go to lower temperatures or lower currents, the conductance seems to go down, and and second, it's much below the quantized value of 2 E squared over h. And okay, on the first slide, I just told you that the conductance should be quantized when we go to zero temperature. So what's up with that? And the reason so there is an explanation for this, which requires strong correlation effects, which were already mentioned in the previous talks. Namely, one can write down an inelastic two-particle backscattering term like this one, which takes two right movers and scatters them into two left movers. And this perturbation is relevant if the Luttinger parameter k of the one-dimensional edge is less than 1/4. And if k is less than 1/4, this term will basically cut the edge into two halves at low temperatures, and it will completely suppress conductance through the edge. And you can derive the conductance through this impurity, and you will get this type of power law times a function of just the ratio of bias voltage and temperature. And the experiment I mentioned indeed sees something like this. If they fit the exponent from here to the data, they get k, which is about 0.22, and also they see this nice function f of only the ratio of bias voltage and temperature. However, I want to point out that this k that they get is very close to 1/4. And it's entirely possible that in a real setup it might exceed 1/4 because in this system that they have, the velocity of the edge state is dependent on the front and back gate voltages, which they use to change the band structure. And therefore also k, the value of k depends on these voltages, and it's possible. I mean, it's so close to 1/4 that it's possible that it would sometimes exceed 1/4, and therefore invalidate the explanation. And also another way to argue this is to take a microscopic formula for k, and if you put in the experimental parameters and you tweak them a little bit, you can easily get values above 1/4. So we wanted to investigate if there is any other mechanism that can explain the this data. And we came up with something, namely scattering from magnetic moments near the edge. And this mechanism doesn't require strong correlations, but k close to 1 is enough. And I will show that the correction to conductance due to a single magnetic moment will have this power law behavior, and now the power is 1 minus k times 2, and this result is valid above some temperature scale T star that I will describe. And if you have many of these impurities, they can lead to this type of insulating behavior with a small power that was seen in the experiment. Okay, so let me first discuss the single impurity case. It's coupled to the edge modes by an exchange interaction, and this exchange is in general anisotropic. And I will assume that the deviation from isotropic exchange is small. So this delta J, which is the anisotropy, is small compared to the isotropic term here. And I will treat this delta J as a perturbation. And if I first just consider the unperturbed Hamiltonian, so the isotropic exchange, so here is the isotropic exchange, and this is the Hamiltonian of the isolated edge, which has the helical modes and density-density interaction, and I will bosonize it. Here is the bosonization identity. In the bosonic language, the exchange term becomes like this, and you see that the spin flip terms S plus and S minus have a different scaling dimension from the SC term, and because of this, these spin flip terms flow differently under RG from this one, and therefore the isotropic exchange becomes uniaxially anisotropic, as you go to lower temperatures. Okay, and the RG equations for this JPerp and JC are here. And in JPerp you have this 3-level term which just comes from the non-trivial scaling dimension. And if we have the initial condition that the Baire value for the isotropic exchange is smaller than 1 minus k, then this first RG equation is dominated by the first term. I can neglect the second term, which comes from Kondo effect. Then in that regime, the RG equation is simple to solve, and you just get a power law for the flow of this coupling, like shown here. And it's okay to neglect the second term as long as we are above a temperature scale T star. And this T star is defined basically as the energy scale where the second term becomes of the order of the first term in the RG equation. And this determines the temperature scale T star, and you see that it's a temperature much less than the Baire cutoff because it contains the ratio, the small ratio rho j over 1 minus k, small by assumption, and it's raised to a large power if k is close to 1, less than 1 and close to 1. Okay, and I will focus on this regime of energies above T star for the rest of this talk. Okay, and we need the anisotropic exchange in order to have any correction to conductance due to this impurity. And the reason is the following. If you have just isotropic exchange or even this uniaxially anisotropic exchange, you see that, okay, first of all, this term doesn't do anything. It doesn't flip the spins. And only the first term backscatters electrons. And when it backscatters, it always flips the impurity spin. So basically, if I take a right mover, it will backscatter, but the impurity spin gets flipped. And because the impurity spin got flipped, the next right mover cannot backscatter because this Hamiltonian doesn't contain terms that backscatter both. And all the right movers just keep going basically cleanly by until a left mover comes and basically reverses the spin. And the net result was that there was no backscatter, no total backscattering current. And there is a rigorous argument to show this that there is no backscattering in this case. Okay, and so basically we need the anisotropy in the exchange in order to have a backscattering. And if you just treat it using Fermi Golden Rule and you assume that the impurity spin is polarized along the z direction, it is polarized because of the isotropic exchange. And Golden Rule gives you basically this result for the average backscattering current. And to find the full temperature and bias voltage dependence, I will insert the renormalized coupling delta J here. And this delta J couples to the spin flip operators which I told you have a scaling dimension k, and therefore these are relevant operators above that scale T star, and they have this power law energy dependence, and you insert this relation into here, and you get the power law dependence for the backscattering current of a single impurity. And if you have many impurities and you just add up the resistances from a single impurity, you will get insulating conductance which has the same power law. And if we compare to the experiment that I showed you, we will find k equals 0.8, which corresponds to weakly interacting electrons. Okay, and this Fermi Golden Rule derivation is not entirely correct. It doesn't capture all the physics. Namely, there is so okay. This is the full exact result for the backscattering current. The first term is basically the Fermi Golden Rule result, which comes from the RG flow of these anisotropic terms in the exchange, and it has a crossover at EV of the order of t, like here. And now there is an extra term, extra factor, that comes if you take into account the dynamics of the impurity spin, which the Golden Rule neglects, because I just said there that we just take a value for the average S. Okay, so this second term comes from the impurity spin dynamics, and it has a small crossover scale, EV of the order of rho j times temperature, and this rho j is a small number, small dimensionless number, because we are above the Kondo temperature. Okay, and this small crossover scale comes from the ratio of basically the effective magnetic field felt by the impurity spin. It's an effective magnetic field, not a real field. It's created by the bias voltage or by the current running along the edge. And there's a second, so it's the ratio of the magnetic field and the relaxation rate of the impurity spin, this Karinga spin relaxation rate. And we have derived a Bloch equation for the impurity spin, and you can get these quantities from basically by deriving the Bloch equation. Okay, so in conclusion, we studied a magnetic moment coupled to a helical edge, and we derived the backscattering current for any ratio of voltage to temperature, and if k is close to 1, you will see power loss around the crossover EV of the order of t, and this provides an alternative interpretation of this recent experiment, where they claimed strong interaction physics. And second point is that a more careful derivation of this backscattering current basically reveals that that there is an additional small crossover scale that comes from the dynamics of the impurity spin. Thanks for the attention.
Questions, please. Moshe?
So you're assuming that everything is above the Kondo temperature and below that the impurity just freezes?
Yeah, pretty much. And there's so there are two temperature scales. There's Kondo temperature, and then there's T star, which is above Kondo temperature.
Additional questions?
Have you analyzed if there are, like in Dimas, two modes of each type related to some exotic Kondo physics?
I don't know.
Okay.
Okay, thank you.